Okay, thank you. Okay. What I want to do, let me spend a few minutes just telling you what I want to do today and tomorrow, what I plan to do. Hopefully it will work out. So I want to talk about, there is an echo. It's okay? Do you hear me? Okay. Okay. So about long-range correlations in systems which are out of equilibrium. And non-equilibrium systems, I mean systems which do not obey, the dynamics does not obey detailed balance, or very roughly, there are some currents in these systems. So I want to do three types of things. One is to look at systems where, and take an example of a system where we know that in equilibrium, long-range correlations are rather not typical. I mean, they appear only near a phase, at a phase transition point. Typically, when we have detailed balance or a system in equilibrium, there's some short-range correlations of particles. You go far away, systems, does not feel what's happening in remote places. On the other hand, at phase transition, you do have long-range correlations, and systems become responsive at very long range. In driven systems, this is the opposite case. That is, the generic picture is that there are long-range correlations. And what I want to do is to consider a simple example of and show how long-range correlations appear. I want to show how they appear in that system. So this is basically would be the first part of the talk. The second part has to do with long-range order. That is, when you have long-range correlations, at some point, you can have long-range order or spontaneous symmetry breaking. Okay? So for example, let's take a very simple system, the lattice, say, with a ring geometry, and take ASEP. So you have particles on this lattice every place. And these particles hop with probabilities P's and Q's to the right or left with exclusion. Okay? So you look at the steady state of this very simple configuration, and you find that eventually the steady state is such that all states are equally probable, right? You have seen that in the talks of Claudio and Gunther the last couple of days. So the density, on average, is basically homogeneous in the steady state. Now, the question is, could you have long-range spontaneous symmetry breaking? That is, could you have a situation in which these particles basically aggregate to a certain place in the circle? So you will have a high-density state on one side and the low-density state on the other. Now, this doesn't happen in the ASEP problem, as we have seen, because it's always homogeneous, independent of the rates at which you have P and Q. So these particles are driven to move, say, in one direction. So what I want to show you that these long-range correlations that appear in such systems can produce long-range order in systems like that. Not in ASEP, but in other models which I want to discuss. So I want to talk about spontaneous symmetry breaking or long-range order in such systems. Okay? So this would be the second topic. And so I'll introduce a model which is not the ASEP and demonstrate how this happens there. And the third subject, and presumably I'll talk about it tomorrow, is heat conduction, anomalous heat conduction. What is this? Now, you know that if you take a system, some particles, and you couple it to heat bath on both sides, say one dimension. This is in one dimension, 1D. And this is T left, temperature right, and you have a flow of energy through that system. Now, you know that typically such systems obey the Fourier law, namely that if you look at the current, the energy current, it should be like K, kappa, some constant, that's the heat conductivity, times delta T over L. L is the length of the system. So delta T is the temperature difference between right and left, and there is a current that is proportional basically to the gradient of the temperature. So when L goes to infinity, the current goes to 0. So that's what typically happens in systems under this kind of configurations. Now, what is anomalous heat conduction? Anomalous heat conduction turns out that in certain quite large number of one-dimensional systems, that doesn't happen. It doesn't look like that, but rather the heat current goes like delta T divided by L to the power 1 minus alpha, where alpha is larger than 0 and less or equal to 1. So it doesn't go like the gradient of the temperature, but it goes like, say, 1 over square root of L, or 1 over L to the 2/3, or some power of L, which is, therefore the conductivity is very large compared to the usual heat conduction that you expect from diffusive systems. People rephrase it as saying, like, you have K times delta T over L, and K is a function of L, and that is K of L goes like L to the power alpha. So it's as if the heat conductivity diverges with the system size, if you try to interpret it as heat conduction. So that I'll do. I'll talk about this kind of systems and how it comes about and what goes into it tomorrow. Today I want to concentrate on the first two things, namely long-range correlations and long-range order in systems which are driven in one way or another. Okay, so basically this is the program that I want to follow. Okay, let me see. Okay, so basically that's what I wanted to see, and let's start. I'll turn off the light. Okay. Okay. So the first, is there a pointer? Oh, yeah, it's okay. Good. Very robust one. Okay. Okay. So what I want to consider is a configuration of local drive. Okay. And there are some references, you can have a look at them there. And okay. The problem is the following. Suppose you consider equilibrium system first, particles on a lattice, and they are hopping. This is basically SEP, okay, the famous SEP that you heard about in last few days. You can take periodic boundary condition, doesn't matter. You have n particles, v vertices. So clearly the steady state is such that the particles are homogeneously distributed in the system with a density which is n over v. That's the probability of finding a particle on a site, on every site. Now let's perturb it. But let's first make a perturbation which is obey detailed balance, namely put a potential on one side. Okay? So either side here, and you put a potential. It could be attractive, it could be repulsive, doesn't matter. Sorry? Okay. Okay. The way you do it, if you put a potential U, basically, since you have detailed balance, this would mean that the transition rate, okay, the transition rates are 1 everywhere except at the particular site, right? Particles hop with rate 1 on each direction, but from that side, side 0, they hop out of it with rate probability e to the beta u, and backward into it with rate 1. Basically, this would obey detailed balance with respect to a potential u on that side. Okay, now, okay, so what is the steady state of the new system with the potential? Now, this system is in equilibrium, so clearly, you ask, do I feel far away, if I stand far away from that side, would I feel the fact that I introduced a potential here? So clearly not. I'm not going to feel anything because there is detailed balance, there is a Hamiltonian. The Hamiltonian is, the energy is 0 everywhere, right? So basically, the particles are, it's a uniform distribution everywhere else except on this particular side. Now, if the interaction is attractive, it will attract a particle there. So effectively, you will have, suppose you put a very deep potential there, it will attract a particle, it will stay there, and the remaining particles, n-1 particles, are going to be homogeneously distributed among all other sites. So in the large n limit, nothing happens, right? Or if it's repulsive, then basically no particle will be there, and V will go to V-1, the number of vertices, nothing happens. The question is, so I clearly don't feel the fact that I make energy perturbation, a potential perturbation on one particular site. The question is, what happens if I perturb it, but in a way that it does not obey detailed balance? Okay? So the way one can do it, okay, that's one way, I can do it in many ways. Suppose you modify the rates, the transition rates from this side to that side, so that going to the right, it will be 1 minus epsilon, going to the left, it will be 1, and everywhere else it's 1. All the other rates of hopping are 1. The question is, if you do that, you break detailed balance now. And the question is, if you stand far away from that site, would you feel the fact that I introduced this kind of perturbation? And what's going to happen in the steady state? Okay, so that's the question. Hope it's clear. Okay, and in fact, since we are talking about long-range correlations, I want to show that, in fact, you're going to feel it very far away. Okay, that's a very different story. So here are the main results that I want to demonstrate in one way or another in the next hour. First of all, if you do it in 2 dimensions or more, any dimension, if you look at the average density profile, the average density before introducing this was right homogeneous. Now, when you introduce it, turns out that the density is going to have a perturbation, and the perturbation is going to behave as that of electrostatic dipole. That is, phi of r is going to decay like the energy, the density perturbation is going to decay like 1 over r to the power d minus 1 at large distances. So you're going to feel it does not depend on n, on the size of the system, as what happened before. It's just a function of the distance. And there's going to be a current. You're going to introduce some currents in the problem, and the currents are going to decay at large distances as 1 over r to the d. So you stand far away, you do this perturbation, and you feel that that's what happens. Now, the same is true basically for any local arrangements of drives. I don't have to actually make a drive on a single bond. I can make modify any number of bonds locally, and if I'm looking far away from that, I'm going to have algebraic decay of the perturbation of the perturbed density away from it. It's not to be a dipole. It could be like a different power law, but that would depend on the local arrangements. But it's going to decay algebraically. So it's long range. There is no characteristic length in the problem. Okay? Then you can ask the other thing, which I'll show. Look at the correlation function. Okay, the steady state correlation function. You look at 2 points, R and S, and you ask, suppose you have this drive at the origin. You take 2 points which are far away from the origin and far away from each other, and you perturb one of them. You ask, what's the correlation with, you perturb at R, what is the effect at S? So the correlation function. It turns out that the correlation function satisfies a different, again, it's long-ranged. It decays algebraically at large distances. But it becomes like a quadrupole in 2D dimensions. That is, if you start with a problem in 2 dimensions, then the correlation function will decay like a quadrupole in 4 dimensions. Okay? And it's going to decay like 1 over R to the 2D, at least when the density is a half. One can show that it's also happened for other densities, because there is the density is the average density. Okay, so these are the results, and I want to show you, it's very simple. I want to show you how you derive these results and what do you get from it. Okay, questions is clear. Okay, so here just to show you, this is the driven bonds there. This is a result of numerical simulations of that. You see that phi, the density is 0.6, the average density to begin with, and you get this perturbation which decays like, this is along the x-axis, along the axis of the pole, it goes like 1 over R. If you probe it in the perpendicular direction, like a dipole, it's going to be like 1 over R squared, but only in the perpendicular direction. In any other direction, it will decay like 1 over R. Okay. Okay. The evolution equation. So let's start, see how it comes about. So this is our line. This is sites 0, 1, 2, and -1, -2. These are the sites. And the hopping rates are 1 everywhere, except, let's do it in 1 dimension just for simplicity, except from 0 to 1. The site 0 to 1, the hopping rate is 1 minus epsilon. And there is this variables, tau I, which are either 0 or 1, whether a site is occupied or not. And you want to calculate what is the tau I at time t plus dt minus tau I at time t. What's the increment of that? If you look at it, then it's going to be the following. You know, if the process is, if tau I was 0, and tau I plus 1, and suppose we are far from the 0 site, from the special site. Let's take just an ordinary site, which is has nothing to do with this modified rate. So you can jump from I plus 1 into I, and this will be modified by 1. Or if tau I was 1, it will become 0 if it could become 0. And this happens with rate dt, with probability dt. And similarly, this is for the process between I and I plus 1. And similarly, between I and I minus 1 could also modify the variable tau I. So therefore, basically, you have these 2 processes that just hopping from the right to site I or hopping from the left to site I and out. Yes?
You have the long-range correlation to the boundary condition still done?
Sorry?
The boundary condition, even if you have long-range correlation, don't change the model?
Well, they could, in principle. Let's take, either infinite or periodic boundary condition. You can take periodic boundary conditions for simplicity so that we don't bother. So this is the only perturbation that you have in the system. Okay? But you're right, if you do something at the boundary, then that could affect, right? But let's take periodic. Okay, so now you average over the stochastic process. So phi I is the average of tau I, that's the average occupation of site I. And you immediately see, as you have seen again in the talks of Claudio and Gunther, that the fact that you have this correlation function, tau I plus 1, tau I, basically they cancel each other. Since this is SEP, the nonlinear correlations cancel each other. And d phi I dt is basically just a Laplacian, right? Discrete Laplacian. And that's a property of the SEP, because it's, okay? So that's very simple. The question is, what happens when you try to write down these equations for the sites either 1 or 0, for the sites that involve this special rate, 1 minus epsilon. So the only thing that is going to be modified is that the rate that tau 0 will hop into site 1 is going to be with the rate 1 minus epsilon rather than 1, right? These are the four rates. The three rates of hopping into and out of site 0 are 1. The other one is just 1 minus epsilon. Okay? Therefore, when you average now, you see that d phi 0 dt, that's here, it's just the usual Laplacian, the discrete Laplacian. But there is another piece that comes from this epsilon there, which involves the correlation function between the occupation at site 0 and 1 minus the occupation at site 1. So basically that's, you need to have this correlation function. So the average density is coupled to the correlation function near that site, or at the site which is involved in the, okay, is that clear? It's a very simple consideration. Okay. Now, the other site, so this is site 0, but the site 1 is also going to be affected by this epsilon because the hopping rate into it is also, does involve epsilon. Here, for site 1, the process from 0 to 1 is going to be affected, and it's with the rate of 1 minus epsilon. And if you just average and sum everything, you see that the d phi 1 dt is again the usual Laplacian minus epsilon times the same correlation function. Okay? That's okay. Now you can do it in higher dimension, of course. It's the same story. It doesn't matter. This is just to demonstrate. So basically, the equation that you end up with is that d phi dt is the discrete Laplacian plus epsilon times this correlation function, tau of 0, times 1 minus tau of E1. This is the E1 and this is 0. That's the two ends of the special bond. Times, but this affects only delta. This is the Kronecker delta. Either R is equal to 0 with a plus sign, and R is equal to E1, this side, with a minus sign. So basically that's the equation. And we need to see what, what's the resulting steady state. So it involves the correlation function. We have to look at it. And therefore, before doing that, I want to consider first a simpler example and get back to this example in a few minutes. And the simpler example, consider non-interacting particles. So it's not, there's no exclusion. Particles can hop to any site irrespective whether there is a particle there or not. So that's the story. Basically, this is going to modify the equation in a way that the hopping rate from 0 to 1, you don't have to obey this. It should not be multiplied by, it is independent of what's happening on site 1. So basically, the only thing that is modified is that instead of having this correlation function, I have here the average of tau 0, which is the density at 0. So that's for the non-interacting case. So for the non-interacting case, the equation is just of phi. It involves only phi itself, that's the density itself, and therefore it's, one can analyze it very simply. So d phi dt is the discrete Laplacian plus phi 0 times delta of R0 minus delta of R1. That's the equation. And in the steady state, where d phi dt is 0, that's the equation. So del squared phi is equal to this. Okay, clear? Okay, so now clear, this is electrostatic problem, right? Phi is like a potential, electrostatic potential with a dipole which is located on the sites 0 and 1. Okay, it's like you have a dipolar charges, two charges, opposite signs on sites 0 and 1. So that's a very simple configuration. Except that, unlike electrostatic problem, the strength of the dipole has to be solved self-consistently. It's not an outside, a charge which is imposed from the outside, but it's proportional to phi of 0, so it's proportional to the density on site 0, and therefore you have to solve it self-consistently. That's the story. Okay? Okay. Okay, you solve it. That's a simple exercise. You solve it. You can do that by looking at the green function. That is, you put a single charge on site on some site R0, and you ask what is the solution of this equation. What is that's the green function. And since it's a linear problem, then phi is just equal to the green function where a charge is placed on site 0 minus the same green function with the origin with a charge placed on site 1. Okay? So basically what you have to know is to solve this equation where you have a charge on a single site okay. Okay, clear? Okay, and this is the Green's function. The Green function of the Laplace equation, discrete Laplace equation in 2 dimensions. Okay, you know what it is. That is, you put a charge on site at the origin, and you define your potential to be 0 at the origin. Then the potential at one site removed, 1, 0. This is the Green function at site PQ, given that there is a charge at site 0, is minus a quarter. If it's 2 sites removed, it's 2 over pi minus 1, etc. Everything is known about this Green function. And what you know is that at large distances, of course, this is a charge. You can take the continuum limit. So it's basically like a charge in 2 dimensions. And the charge in 2 dimensions, the potential is just logarithmic. It just decays. It just goes logarithmic with the distance from the charge. Okay, that's in 2 dimensions. In higher dimensions, it's whatever. Okay, so basically the solution, our solution for the density, is just rho. That's the average density plus epsilon, the phi 0, whatever, and then we have the Green functions, which we know already. Okay. Now, how do you determine phi of 0? That's very easy. You take, this is the equation. You write down the equation for r is equal to 0. For r is equal to 0, you know that g0, 0 is 0. g0 E1 is minus a quarter, just from the table that I showed you before. And therefore, that gives you that phi of 0, that is the strength of the dipole that you have to consider, is just proportional to the density, of course. That's the average density in the system. But then it is also involved epsilon. Okay. Okay, so that's okay. Epsilon cannot be too large, so don't worry, this cannot be negative, the denominator, because the rate is 1 minus epsilon of hopping in one direction, so epsilon is less than 1, so no problem. Okay, so what happens at large distance? So now we know what the charge is. We know the charge, this is the potential. Therefore, phi of r at large distance is basically, the Green function is log, so the difference between these two Green functions is just, you have to take the derivative, and the derivative gives you just 1 over r squared here, and the dot product of E1 dot r. So if in any direction in which is not perpendicular to E1. E1 is the direction of the dipole. It goes like 1 over r. In the direction which is perpendicular, it will go like 1 over r squared. You also induce currents in the system. And the currents basically are the derivative of the gradient of that, because everywhere else, except on the dipole itself, it's just diffusion. So the gradient is the current, so it goes like 1 over r squared rather than 1 over r. Okay. Okay. Now, what happens when you have more than one driven bond? Okay. So suppose you have, some configuration which is like that. Then clearly, again, for the non-interacting particles, we'll get to the exclusion process shortly. Then it's just a linear combination of those. So basically, it's you have a dipole at site 1, a dipole at site I2, etc., etc. You have to just take the sum of those. And the charges which are there, the strengths of the dipoles, it's not just you have phi of I1, phi of I2, etc., and you have to solve them self-consistently, these charges, which you can do because you just write down the equations for of phi of r for the sites E1, I1, I2, I3. You get a set of equations, and you get just a set of equations for the charges. You can solve them. It's a linear equations, and you get what happens. Okay. Now, clearly, you get a electrostatic potential far away. If all these bonds are localized in some region, you get some electrostatic potential far away. And depending on the configuration, it could be dipolar, it would be quadrupolar. It depends on the moments of these charges that will develop there. Okay? For example, if you take these two bonds, like rather than one bond with minus epsilon to the right, it's also 1 minus epsilon to the left. This will produce a quadrupolar arrangement. So the density far away is going to be that of a quadrupole. Right? Because each dipole, this dipole produce plus minus. This one produce plus minus plus. So it's as if you have charges of 2 here, minus 1, and it's a quadrupole. Yeah. Okay. Okay. Now, in higher in dimensions which are not equal to 2, in one dimension the potential, the phi, the density, is going to be a step function, actually, because the green function is just absolute value. If you put one charge, the electrostatic potential of a charge in one dimension is just the absolute value, and you have to take the derivative of that, and basically you get a discontinuity of the potential in very large system. On the other hand, if d is larger than 2, then it just goes like 1 over r to the d minus 1. Okay. Okay. Now, I want to get back to the model with exclusion. Now, having this in mind, we have this equation to solve. Now, what you see is basically the same problem, except that we don't know what is this correlation function. We need to solve for the correlation function. But it doesn't matter. It's a number. We don't need the whole function of the two-point correlation function at any sites. We just need the two-point correlation function on side 0 and 1. So it's a number. So unless it is 0, which typically it is not, then we get back the same problem, except the strength of the dipole is not going to be determined by this equation. We have to determine it in some other ways. So that's so even when in the model with exclusion, we still have the same story, that you have a density which is decaying to the average density with some algebraic profile, like a dipole in the dimensions. Okay. Okay. So that's the same story as before. I want to show you here just a result of simulation. Just that this is the case of non-interacting. This is the density, basically, as it decays along the axis of the dipole on a logarithmic scale, and it goes like 1 over r. Similarly, this is for the case of interacting, namely the with exclusion, and you measure the correlation function between side 0 and 1 numerically. You fit it, you see it fits very well. Everything works well. Now, there is also a magnetic field analogy. You see here there is an analogy between the density and the electrostatic potential. I want to show you that magnetic field is going to correspond to currents. Okay? So let me just spend a few minutes on that. Let's do the following. Suppose you have a bond here, and the hopping rate from here to here is Eij, and going backward is Eji. Okay? So I'm going to define a magnetic field. Why I'm doing it in a minute. So with the process I going from I to j, I take the log of Eij, and I define it as a magnetic field in the two plaquettes that are adjacent to this bond with the convention of the right-hand analysis. That is, it's going, up here and down there. Okay? Similarly, for j to I can do the same thing and reverse it. So basically, the net magnetic field, which is produced by this bond, is just log of Eij over Eji, right? Because I am reversing the direction. Okay? So now I give you some configuration of bonds, and I ask you what is the magnetic field everywhere. For example, suppose I make a bond here that go, bias to go this direction, that, and that. Now, if you look at it, you have a dipole. Let's look at the charges. The dipoles are in this direction. There is a dipole in this direction, this and that. therefore, the net charges is 0 because the minus charge of this dipole is going to cancel the plus charge of that dipole. So basically, there is no charge in the system. No charge means that the density is flat. It's like you have a Laplacian. The equation of for the density is just Laplacian, just equal to 0, and because there is no charge. Okay, is that clear? On the other hand, there is a magnetic field because there is a magnetic field from this bond which goes up here and down there. The magnetic field from this bond is also up here. So all the magnetic fields from these 4 bonds is all up in the middle and down in the other side. So there are magnetic fields, which means that there are currents. Magnetic field is associated with current. So there are currents, which is circular currents, but there is no density profile. The density profile is flat. Here, it's the opposite case. That is, if you make bonds that go in this direction, biased in that direction, then here you have a charge of 4, while you have a minus charges on these corners. So there are charges, and there are therefore density profiles which decay with some power of R. On the other hand, the magnetic fields are 0. Because the magnetic field here in this plaquette, which is induced by this bond, cancels the one which comes from this bond. And therefore, there is no magnetic field. No magnetic field means no current. And in fact, this configuration corresponds to the case where you have basically a potential, just a potential on side 0. It will look like that. So it's equilibrium, detailed balance, just perturbing it with a potential. Okay, so in general, non-zero electric field, you get inhomogeneous density with power law decay far away. Non-zero magnetic field corresponds to current, and zero magnetic field everywhere means equilibrium configuration, no currents, and that's detailed balance.
David?
Yeah.
Could you explain why did you put that as magnetic field?
Here, yeah. I'm going to do it now. Why this is the definition of a magnetic field. Okay, how do you decide? Suppose I give you a system, and that's what's known as the Kolmogorov criterion. Suppose I have some set of configurations, microscopic configurations, which I call C. It could be configuration of SEP or TASEP or whatever system. And you have transition rates between C and C prime. I give you the transition rate. And I ask you, does this satisfy detailed balance? Okay? You don't really know what's the steady state. So you cannot really check whether there is the detailed balance condition is satisfied. But I just give you the rates and ask you, does it satisfy detailed balance or not? So there is this criterion of Kolmogorov which says the following. Suppose you start with some microscopic states, okay? These are microscopic configurations. Call them 1, 2, 3, 4. They could be microscopic configurations of whatever, many particles, on a very complicated space. And suppose you make a transition from 1 to 2 to 3 to 4, and then you make a circle, go back to 1. Take any set of configurations and go back. And you look at the product of the rate going from 1 to 2 times 2 to 3, 3 to 4, and then go back to 1. So that's on the left-hand side. Then take the product of the rates going backward, okay? From 1 to 5, whatever. If these two products are the same, for any cycle you can think of, then you have detailed balance. That's the criterion. So basically, that's what happens. And if you look, for example, so that basically that's why when H, the magnetic field is equal to 0 everywhere, then you satisfy this criterion and you have a detailed balance, no current, because H is just the sum of EI, I plus 1 divided by EI plus 1 go to I, and then you have to sum it over all the chain that goes from one to the other, which means that basically that the product of the EIs going in one direction is the same as the product of going EIs in the other directions. And if this happens for every cycle that you can make, then you have detailed balance, no currents. So that's the, okay. So this was it. Okay. 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 Now I want to move further, and I want to consider correlation functions. So now we are equipped with this analogy to electrostatics. Then it becomes more complicated, but I want to consider the correlation function. Okay. What is the correlation function? I want to look at the correlation function, which is the average of tau r, tau s, minus the product of the averages. Okay, I have to take 2 points, r and s. Typically, I am interested in far away from this dipole. I mean, again, it's a single site which is driven, and I want to look at what happens there. Now, let's go first to one dimension, and this was a problem considered by these people some time ago. What they have shown. Okay, first of all, this is the density profile, right? In one dimension, in a finite system of length L, you have a discontinuity of the density at the site near the bond, around the bond, which is driven, and otherwise you have a linear profile. Okay, when L goes to infinity, basically this linear profile becomes flat, completely flat. That is, it becomes flat here and there. Now, they have shown that in this case, the correlation function has a scaling form which looks like that. It goes like 1 over L in a hydrodynamic limit. It's a function only of I over L and J over L, and it goes like 1 over L. So when L goes to infinity, the correlation function goes to 0. So 2 sites in the large L limit, 2 sites become uncorrelated in the large L limit. Because, why? That's because in the large L limit, the density profile looks like that. So basically there is no current. J is equal to 0. Right? When L goes to infinity. And when J goes to 0, it's basically, they don't feel each other, and the correlation function goes to 0. Okay? Now I want to consider it, say, in 2 dimensions to see what happens. Now here, you expect something else. Okay, so let's look at the following problem. I have to apologize. I changed a little bit notation here. The bond, this special bond that is driven, I take it 1 minus epsilon in this direction and 1 plus epsilon in that direction. It really doesn't matter. It just, there is some symmetry which I want to exploit here, and therefore it's easy. I could have done what I've done before with this minus epsilon and plus epsilon. It wouldn't matter at all. Okay? So that's so the driven bond is between -1 and 0, and the rates are symmetric in this way. Now here, when you take the thermodynamic limit, that is when L goes to infinity, currents do not go to 0, unlike one dimension. In one dimension, since currents have no way to escape, I mean, it's a one dimension, they have to go only in that direction, and when L goes to infinity, the density becomes flat and the current is 0. Here, you are going to have currents which do that, locally. And they are going to decay with a function of R. So the correlation function need not go to 0 in the thermodynamic limit. It's just some number, some function of R. Okay? So I want to look at that. Okay, so I want to show you the following, that when you look at this correlation function and you write down the steady state equation for it, it's going to have the following form. Now, this C of R and S, it's a function in 2D dimensions. So if we started with 2, this is a function in 4 dimensions, right? These 2 points, R and S. So basically, if you take the Laplacian operator on this function in 4 dimensions, it's del squared R and del squared S. Okay, so it's a Laplacian in 4 dimensions, if we talk about 2. The equation it's going to satisfy in the steady state is that this Laplacian of this function is equal to something, which I can look at it as a charge. Okay, so there is an equation, okay, and I will talk about this charge. It's a sigma of R and S. There is this charge which is distributed in this 4-dimensional space, and it satisfies that. And if the charge is localized someplace, then I can infer what's going to happen with this correlation function, right? I have to analyze the charge, basically. That's the story. So this is the equation. Why is this the equation? Let me just demonstrate it very simply. For example, let's take 1 dimension for simplicity, just to look at. And first of all, let's consider I and j. Let's take 1 dimension. Take I and j, which are not 0 and 1. I want to be far away from this special bond. Okay. So basically, if you look at, I want to calculate tau I at time t plus 1 times tau j at time t plus dt minus the tau I, tau j at time t, right? Which is equal to basically tau I at time t plus dt minus tau I at t times tau j, right? It's just derivative, and then tau I times the derivative, the time derivative of tau j. Okay? Now, and if you take the average, so basically we know that for in this 1 dimension, this is equal to Laplacian. That's what we showed before, right? That tau I of t plus dt minus tau I of t, this is equal to this, where here I just omitted the label t. They're all at time t. All these tau i's, I minus 1, this is tau j is at time t, and this is at time t. So basically, it's a Laplacian of tau I times tau j, and this is a Laplacian of tau j times tau I. Now, if tau I and tau j are not close to each other, so that not close, I mean that tau I is never j plus 1 or j minus 1 or j. This is just the correlation function, because I can put it right. So basically, it's the Laplacian of the correlation function with respect to I, and this one is the Laplacian with respect to j, and that's the equation. Okay. And similarly for now, when is it going to be modified? It's going to be modified in the following points. When, first of all, when I is equal to either j or j plus 1 or j minus 1, okay? Then then this is not going to be, if I is equal to j plus 1, then this is not the correlation function, because it's just tau squared and something else. It's going to be modified a little bit. It's also going to be modified if I'm close to the drive, that is 0 and 1. Okay? And that's where the charges are going to be. So here is where the charges are. Just so they're going to be okay. This is R and this is S. So whenever R is equal to S or plus minus 1, you have some charges. So that's one. This is R is equal to S. And whenever R or S are 0 or 1, I'm going to have some charges. So this is the charge distribution. It's going to be distributed in a very, on these manifolds. Okay, this is just pictorially, I use R1 and S1. Remember, R and S are 2-dimension each one. So I just make suppose R2 and S2 is equal to 0, and I just cut in this plane, just to show you where. But actually, these are planes. Okay, so you have these charges. Okay. Now, you have to analyze these charges. And that's not, okay, this is a bit tedious, but you can use, but let's assume for a minute, let's go back. No, here. Let's assume, which is the case, that these charges are going to decay at large distances. So basically, they are concentrated around the origin. Okay, so it's localized, basically. It decays with some power law. Then I want to use basically symmetry arguments to see what kind of are these charges, do they have a charge, a dipole, a quadrupole? What's the symmetry that I'm going to have? So let's consider the symmetry of the problem, okay? So you have the correlation function. Now, this correlation function obeys the following symmetry. Suppose I invert epsilon. That is, remember, epsilon was this. So basically, I make an inversion. When I make an inversion, epsilon goes to minus epsilon because I just invert the directions. So if I invert epsilon and make an inversion, r goes to minus r and s into minus s, it's the same problem. And therefore, C has to satisfy that C of epsilon, that is given epsilon, of r and s is C of minus epsilon minus r minus s. There is this symmetry. Then there is also particle hole symmetry. That is, if I change the notation that particle is a hole and the hole is a particle, so I go from rho to 1 minus rho, right? And invert epsilon, that's going to give me the same correlation function. That's, again, the symmetry of the problem. So that for r is equal to 0, for rho is equal to a half, when rho and 1 minus rho is the same, there is it's symmetric with respect to epsilon, right? Also, you can convince yourself right away that if you integrate over the correlation function over r, it's going to give you 0, because when you integrate, for example, over r, integral of tau of r is just the number of particles, right? So you can take it out, and the rest will give you 0. So these are properties of the. Okay. So the consequences of the symmetry. The consequences are the following. I mean, if you look at these charges, they always come with a plus, minus. I mean, the net charge is 0. For rho is equal to 0, for rho is equal to a half, we know that we have this inversion symmetry. And therefore, it does not support a charge if it has a periodic boundary condition. It cannot support a dipole if it has at rho is equal to a half, because it has an inversion symmetry, right? A dipole with inversion symmetry will go to minus itself. And therefore, the leading term that can appear is a quadrupole, which obeys all this symmetry. And therefore, we expect that that's going to happen here. So C should go, the correlation function should go like a quadrupole in 2D dimensions, So 2 goes to 4, 3, 6, etc. For rho is not equal to a half, you can show that the same is going to happen to leading order in epsilon. So I will not go into it. I want to, but it's true also, and I believe it's true for any epsilon, but we couldn't prove it, that the leading is indeed quadrupole. I will not go into it. Okay, so what are the charges? Just to show you what are these charges, what they involve. They are distributed on these planes. And here, just to show you what the equation is. This is the equation that the Laplacian of C in R and S is equal to 3 sets of charges. Sigma 1, which we call sigma 1, sigma 2, sigma 3. Sigma 1 is these charges, sigma 2 is this, and sigma 3 is that. And what do they involve? They involve the correlation function itself. Okay, again, like we had with the density, you have to solve it self-consistently. The charges themselves are the correlation functions, involve the correlation functions on these planes. Okay? And you have to solve it self-consistently. And to demonstrate that indeed it's localized, which you can show self-consistently, and therefore this conclusion is hot. Okay? But I don't, just to show you what, these are you see, the sigma 1 are the charges when R is equal to S. That's the diagonals, RS or S plus minus 1. These are the charges when S is equal to 0 or R is equal to 0. So this is close to the drive. And this is also close to the drive. You see, the upper ones does not involve epsilon, because epsilon, it has nothing to do with the drive. It's just the fact that R is equal to S, while these two involve the epsilon itself. And okay, but just to show you how it goes. Questions? Okay, so let me summarize this part. So this is the first part of long-range correlations, how they appear in such systems. Oh, and of course, you can think of other kinds of drive. You need not be local. You can drive it from the boundary. You can drive it from in the bulk, like ASEP, or models, which is based on that. And basically, generically, you do generate, unless you have particular reason, you do generate long-range correlations. So at least local drive produce density profiles. They produce correlations so that when you perturb a system one place, you feel it very far away, and you can demonstrate the way it happens. Okay? Questions so far? Okay. Now I want to go to a different, to go to the problem of spontaneous symmetry breaking in one dimension. Okay. Typically, in one dimension, okay. In one dimension, when you have in equilibrium, you don't expect to find long-range order, right? And the typical, the very simple argument is the following. Suppose you consider a simple model of variable sigma, which is plus or minus 1 on site I. I is just one dimension. Is a lattice in one dimension. And suppose you start with a state, okay, and you get energy, which is just Ising model some sigma I plus 1, nearest neighbor Ising model. That's the simplest possible thing you can think of. And suppose you start with a state which is all plus. Now, how does and at some temperature T, right? Equilibrium, okay? What's the simple argument that it cannot sustain a state which is predominantly up? The simplest argument, you can prove it, but you can just to argue very simply, you say the following. I start with dynamics, say Glauber dynamics. I try to flip spins with some probabilities which obey detailed balance. So at some point, I'm going to generate a droplet of minus someplace, okay? Okay. Now, once you generate the droplet, then flipping this spin is going to cost you nothing, right? Because it's adjacent to minus and to a plus, you flip it. And basically what's going to happen, and once you flip it, this could be flipped. And therefore, the length of this droplet is going to make a random walk. It doesn't cost any energy to expand or shrink, okay? And therefore, eventually, this whole state is going to be destroyed. So that's why you don't have long range. And it's a very general argument. You don't have to, it could detect any short range interaction. It will do it. On the other hand, in higher dimension, this doesn't happen, because in higher dimension, if you start, you look at this model in higher dimension, we start with states, everything is plus, and you try to make a droplet of minus. The energy cost of the droplet is proportional to the perimeter, right? And therefore, larger droplets cost more than smaller droplets. And therefore, if you look at the equation for the radius of these droplets, say r, it's going to go like sigma. Sigma is the surface tension, 1 over r. It's going to decrease with time. And therefore, you generate droplets, and if it's small enough, it will just shrink. And therefore, at small enough temperatures where you don't generate these droplets at high rates, you know, this state of predominantly plus will maintain its identity, right? Because you generate droplets, but they will shrink at low temperature. At high temperatures, you generate many droplets, and therefore at some point they can cooperatively join hands and flip the whole state, and therefore you lose order, right? But as long as you're at low temperature, you can maintain long-range order. Not in 1D, because in 1D, the energy cost of this is just 1, independent of the size, okay? Okay. What's the way to generate in equilibrium long-range order in 1D? You need long-range interactions. You need long-range interactions. That is, for example, if you take again with the Ising model, if I consider J, which is a function of R, and sigma I plus R. Suppose you have interaction not only nearest neighbors, but it's sum over I and sum over R. Okay? And if JR decays sufficiently slowly, you do generate long-range order, right? For example, if J of R goes like 1 over R to the alpha, then if alpha is between 2 and 1, you do have long-range order. It's because you can repeat this argument, and that's a nice exercise. You take a droplet, calculate how much does it cost you to flip it to a droplet of size L in a system of size capital L. You ask how much does it cost. You have to integrate all these energies. You do that, and you see that if alpha is between 1 and 2, it costs you energy, which is a power of the size of the droplet. And therefore, it doesn't pay to grow, and therefore you can shrink it, and that's how you generate long-range order. That's the usual, okay? Now, what I want to do is to take a one-dimensional model which is not in equilibrium with everything local dynamics. Okay, that's the whole thing. I don't want to go to long-range interactions or long-range processes, but local dynamics. And I want to see how long-range order or spontaneous symmetry breaking is generated. Okay. So here is the model. It's a generalization of the ASEP. So let me, okay. Okay, it's called the ABC model. We call it the ABC model. When we have seen that for the ASEP, where you have only particles and holes on a ring, that the density is always homogeneous. So I want to generalize this ASEP into a model which has three kinds of particles. That is, particle hole is, I call it two kinds of particles, a particle and a hole, right? That's a two, okay, A and B. But here it's A, B, and C, okay? And I want to define the dynamics on this set of states, okay? You have a ring, and with particles of three kinds of particles, A, B, or C, and they hop, they flip nearest neighbors every now and then. So I take, the process is that the dynamics is I take a pair of nearest neighbors and I flip them with some rates. Okay, pretty much like I do for the ASEP, except that they have three kinds of particles. Okay? And here are the rates, okay? Suppose I go, say, clockwise. So the dynamics is, if I have A, B, so I go clockwise. So A, this is A, and this is B. Then I flip it to BA with rate Q. And if it's BA, I flip it with rate 1. That's the story. Similarly, if I have a BC, I go to CB with rate Q and 1 in one direction, and CA, Q and 1. That's the model, basically. And Q is some rate. For simplicity, we can take it smaller than 1. If it's larger than 1, it's the same. There's some symmetry. So let's say Q is smaller than 1, smaller or equal to 1. Now, clearly, if rho is equal to 1, if Q is equal to 1, then it's fully symmetric, right? It just do diffusion. It does diffusion. And the resulting steady state, I mean, is just fully mixed ABC, right? If you look at the density of locally, they are going to have, each one is going to have its own density, okay? So it's fully mixed, it's a fluid, nothing interesting. The question is, what happens when Q is not equal to 1? Okay? Does it stay fully mixed, or is it going to phase separate? What is phase separate? Phase separate means that I'm going to have regions where are predominantly A, or more A's than B's. And by regions, I mean macroscopic regions, not local. But the question is, when I take n to infinity, that is large system, will I get a bulk phase which is predominantly A or B or C, so they have phase separate. This would be symmetry breaking. This would be long-range order. Okay? And what I want to do is to demonstrate that in this model, phase separation takes place. In fact, not only that it takes place, you cannot get rid of it. In a sense that any Q which is not equal to 1 will produce phase separation. Okay, and that's because, again, you have effectively what's going to happen, and I want to talk about it, is you generate in some very indirect way long-range interaction. If you try to describe it as equilibrium problem, you generate long-range interactions, and long-range interactions can produce long-range order in 1D. Okay, so that's the program. The model is clear because it's the model is very simple, and really you can try the dynamics in your head, I mean, what's going to happen, and you'll see what's the mechanism that happens. Okay. Let's first take a simple argument, and then we can prove things in certain limits. So these are the rates. Now, suppose you have let's look at a particle which is placed to the left of C's. Okay, there is A, and then to the right of it there are, a domain of C's. Now, okay. Now, if you have AC moves into CA with weight 1 and backward with weight Q. So basically, this A is going to move into the C with velocity which is 1 minus Q. Right? It goes to the right with weight 1 and backward with weight Q. So with a very fast, it's a finite velocity, if Q is not equal to 1, you will end up with this kind of configuration. Similarly, if you have C placed to the left of B's, the C is going to move with velocity 1 minus Q into the B's, and it will end up in the other side. And similarly for B to the left of A's. Okay? Okay. So that's the basic processes that are going to take place. So let's start with some random configuration. So this is random configurations of A's, B's, and C's, and of course, the number of A's, number of B's, number of C's is conserved. Okay. So what's going to happen? What's going to happen is, for example, look at this C. This C is not really happy with where it stands. Why? Because if it moves, switch into the B, C and B, the C wants to go into the B and with some finite velocity and find itself there, right? It could have gone into the A's similarly, but it doesn't matter. It will choose either to the right or to the left because C doesn't like to be on the right of the A's either. But once it's flipped, say it went here, then from this time on, it will just move with a finite velocity into that direction. Okay? So what's going to, and this process is going to happen at a very fast rate because it happens with a velocity. It has a finite rate of happening. So eventually, what's going to happen that after a very short time, you are going to have, rearrangement of this configuration into A's and then B's and then C's. A's, B's, and C's. Small domains of A's, B's, and C's. Then they are happy. Everybody is happy. So that's what's going to happen. Now, but this is not phase separation. Phase separation is when you have a macroscopic domain of, predominantly A or B or C. This is just small domains. This is local arrangement. Now, so what's going to happen now, after this fast rearrangement process, you're going to have a slow coarsening process, okay? And the coarsening process is the following. You see, this B is okay. It's happy with where it is, but with some probability, it could hop over this domain. I mean, it could hop here with rate which is Q cubed, right? Because each time it goes around the C, it has the rate is Q, and therefore with a Q cubed, it will end up here. But it's going to happen. It's a fluctuation, but it's going to happen if you wait long enough. Once it finds itself here, then it's not really happy here. It could just go through the A's and join the B's because B does not like to be to the left of the A's. So it could go. Clear? It could have gone backward. right? But there is some probability that it will go forward. And once it's here, then it gets stuck. So if you wait long enough, basically these C's will cross the A's and eventually join these C's there. And you get a coarsening point. Once they disappear, by the way, once these C's disappear and they join this, then you have BA adjacent to each other. BA don't like to be adjacent to each other when B and A. They like to be A and B. And therefore, they are very fast, will cross each other. And therefore, basically, you're going to lose a triplet after these C's overcame their barrier of going to that side. Then you get a fast rearrangement, and you get a coarsening process where triplets are going to disappear, and they merge with the neighboring triplets. Okay? So eventually, what's going to happen, this is going to take longer and longer and longer, but eventually you're going to have a phase separation, phase separate state.
It's not going to be like 3 groups, right?
Sorry?
It could be a few groups, right? Not just 3 groups, A, B, and C.
Well, the A, B, and C, if you wait long enough, eventually that's what's going to happen. You have as a metastable states, you can have, large A, but eventually the 3 groups, okay. But there are fluctuations, that is, there are going to be 3 groups. But of course, at the boundary, there's going to be some mixture because there is probability of going back and forth. The point is that when this B is become macroscopic, it's very long, the probability of this A crossing this whole thing is exponentially small, exponentially in the length. And therefore, it will never do it, basically. And it will just mix. There is some domain of finite size where you have some mixture. But in fact, it's a very strong phase separation. It's strong in a sense that if you are deep into a B phase, your chance of finding A or C is exponentially small.
So does that mean it also remains static? It doesn't rotate or anything like that?
No, it's not going. No, maybe on an X. It could on. It will not rotate because there is no sense of going right or left. So take it back. Take it back. It depends on the densities. You see, there are 3 conserved densities, which are the number of A's, number of B's, number of C's. So, if the 3 densities are equal, then the chance of this B going in this direction is the same as the chance of this B going in the other direction. So if it rotates back and forth, it's at a very small rate, exponentially small rate, but it goes back and forth. But if, say, the number of A's is smaller than the number of C's, then it's clearly going in this direction is going to be easier. Okay, but okay. 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 So as I said, the model exhibits very strong phase separation. In fact, one cannot get rid of it in a sense that this is for any Q. It doesn't matter. A Q is just as long as it's not equal to 1. Also, if you look, for example, at the boundary here, the probability of this B going into this C is at a distance L, little l, here is Q to the L, right? It has to overcome this barrier of Q to the L. So basically, the density into these B's, into the C's, is exponentially decaying, okay? With a length which is log of Q, or 1 over log of Q, because the density goes like Q to the L, okay? So that's Now it's a, how am I doing with time?
5 minutes.
Sorry?
5.
5 minutes, okay. I'm going to get into, okay. At least I'll start, I thought I would finish it, okay. Okay. Now can you demonstrate this in a more rigorous way? But the argument is very convincing. I mean, that's clearly what's going to happen there. And it turns out that there is a special case for which you can demonstrate it in a clear way. And this is a case where the three densities are equal. So suppose the number of A, B's, and C's are the same. That's the story. Okay. Okay. Now, this is very special point, and it turns out the following happens. That, in fact, for this case, where the three densities are equal, you can write down the dynamics for any Q, arbitrary Q. Okay, Q is whatever it is, which has detailed balance. Okay, although there is Q, I mean it's biased. Okay, but you can write down and demonstrate that in fact these dynamics obey detailed balance with respect to some Hamiltonian. Okay, which I'll write down explicitly eventually. So basically, I want to show the following: that in the steady state, suppose you start with a configuration X. What is X? X is just a series of A, B's, and C's on the lattice. Okay? So that's a configuration. The probability of having this configuration in the steady state is given by the following. I can define a function E of X, just number, basically it's the energy. I call it the energy, it doesn't matter. Some number associated with it. And the probability of seeing these microscopic configurations is go like Q to the E. Okay? So it's as if there is an energy, with quotation mark, of the system. Each configuration has some energy, and the probability is Q to the E. So basically, it's E to the power ln Q times E. So ln Q serves like beta, like 1 over temperature. That's minus 1 over the temperature. Right, so the temperature is infinite when Q is equal to 1, so everything is, you lose everything. But as long as log Q is not infinite, it's a finite number, then that's the probability. And now all I have to do is to tell you what E of X is for this case. Okay, let's start doing it, and maybe tomorrow we can. Okay, let me just say what it is. Tomorrow we'll continue from there. I do the following. I define energy in the following way. I start with a case where A's, B's, and C's are fully separated. Okay? You have A's, and then all the B's, and then all the C's. And they assign it an energy. Energy equals 0. Okay? Arbitrary. Okay, then I do the following. I look at this configuration, and because A, B, and C, they are happy, right? Everything is happy. That's the ground state. That's they want to be in this order. Now, suppose I take A and B, and I flip them. Okay, I get a new configuration. Whatever is to the right and to the left. But I take AB and turn it into a BA, and I assign it an energy. If I do that, I assign it energy plus 1. So each time I keep on flipping, and each time I flip in the wrong direction. There is a right direction and there is a wrong direction. If I flip BA into AB, I reduce the energy by 1. If I AB into BA, I increase the energy by 1 because AB likes to be AB and not BA. Okay? And similarly for CA and BC, and I keep on flipping. And by doing this flipping, and I assign energy, I get configurations and assign energy to these configurations. Okay? Do that. You can show that, in fact, if that's the energy, then there is a detailed balance with respect to that energy in a sense that the probability of this having a configuration with AB times the rate of AB going to BA, which is Q, is equal to the probability, steady state probability times this probability is 1, and it obeys detailed balance with respect to that, so that P of x eventually is going to be Q to the power E of x. Okay, so let's stop here, and then tomorrow I'll just wrap it up, and then I want to go to the anomalous heat conduction. Okay.